This is Hsien-Yi, and then I'm gonna talk about photophysics and the photoelectrochemistry of semiconductor materials for energy applications today. Okay, so in terms of this topic, I'm gonna talk about what we have done and what I'm gonna introduce today. So actually, the materials we focus include organic compound, inorganic compound, hybrid materials, including functional metal polymers, hybrid perovskite, and the metal-based polymers. Okay, and then when we design or synthesize these materials, we will systematically investigate the photophysical and the photoelectrochemical properties by ultra-fast transient absorption or time-resolved photoluminescence. In terms of the photoelectrochemical properties, we usually use the potential state and the scanning electrochemical microscope imaging, or a modified SECM imaging we call the scanning photoelectrochemical microscope imaging, in combination with the computational simulations. Okay, and then at the same time, we have to characterize the materials we design or synthesize by the common method such as NMR, TEM, SEM, XRD, XPS to make sure the produced materials is what we expect. After the detailed characterizations for materials for the photophysical and the photoelectrochemical properties, we will determine what kind of applications is suitable for those materials we design. Okay, so it really depends on the photophysical and the photoelectro properties. The applications for the materials we design are for solar fuel generation, for solar to electricity conversion. Sometimes we make the biophotoelectro to convert the energy from the waste, either the food waste or the wastewater. And some of the materials we design shows efficient charge recombination, which means those kind of materials are beneficial for light emitting device. And then in my research work, I focus on electrochemoluminescent device, and then I will introduce those later. And just want to give you some example how we use this scanning electrochemical microscope. Okay, we use this photoelectrochemical techniques for the design or for the synthesize the new materials. So here is one of the hybrid perovskite. And then as you may know, the hybrid perovskite with the chemical formula of ABX3. So the amount of the hybrid perovskite is enormous. So we use this high throughput scanning electrochemical microscope to screen out the potential hybrid perovskite for the further studies. So in this case, we try to develop the non-toxic tin-based hybrid perovskite, and then we make the tin-based hybrid perovskite with different compositions. And finally, we use this SECM imaging technology to scan this photoelectric array, and then finally we can find out the perovskite with the highest photoelectrochemical response, such as this, and then we can confirm this perovskite candidate for our next step. So as I mentioned, we generally study the photophysical and the photoelectrochemical properties. For example, we study a series of hybrid perovskite with a different amount of lead iodide. And then we found when we add 2.5% excess lead iodide, it shows the longest diffusion lifetime. Therefore, leading to higher power conversion efficiency. Okay, and then as you may know, the pristine hybrid perovskite, sometimes the performance is not good enough. So we have to use the diverse method we call the morphology engineering, including additive engineering, humidity engineering, solvent engineering, composition engineering, etc., to further optimize our newly developed hybrid perovskite. Last year, we used the heterojunction engineering to produce in situ formation of the heterostructure of the bismuth-based hybrid perovskite. Due to this heterostructure of a bismuth-based hybrid perovskite, this can get leads to the efficient charge separation due to the energy level alignment. Okay, for what? For the hydrogen production. Another work, we try to develop a new method to increase the stability of the photoelectrode. This is MIS photoelectrode, metal insulator semiconductor photoelectrode. This MIS photoelectrode has been widely studied for a long time. Why this MIS photoelectrode is important? For example, we generally use silicon as the semiconductor. However, the silicon is easily to be oxidized to produce the silicon dioxide. It's not conductive. Therefore, in order to prevent the oxidation of the silicon semiconductor, we usually coating insulator. Sometimes we use aluminum oxide or titanium oxide, and then use catalyst, the metal catalyst for the water splitting. However, if the insulator is too thick, the conductivity gonna be decreased, leading to the poor performance. But if the insulator is too thin, the stability gonna be worse. Therefore, we develop a new method called the localized breakdown process. After this breakdown process, we can create a conductive pathway, as I show you guys here. So by this way, we can increase the thickness of the insulator. And then after treating by this localized breakdown process, we can produce this conductive pathway. In other words, we can increase the stability by increasing the thickness of the insulator, and simultaneously enhance the efficiency by the breakdown process due to this conductivity pathway. Okay, so after briefly introducing my work related to photophysical and photoelectrochemical properties for semiconductor materials for energy applications, Now I wanna show you guys some examples. Today I will introduce two kinds of hybrid materials we are working on. The first one is functional metal polymers. The second one is organic inorganic perovskite semiconductor. Okay, so as you may know, there are diverse metal polymer materials, and then I'm gonna focus on this we call platinum acetylide polymers. And then this time I will introduce the light emitting device, one of the light emitting device I'm interested in, called electrochemoluminescence. Okay, we synthesize and develop these platinum satellites, abbreviated by PTT, PTP. Why we design this platinum satellite? Because we want this valve as the electron acceptor, and then the phenolic group as the electron donor. So the energy gonna be trapped to this dolphin group. Okay, and then this platinum satellite, they have two kinds of formation. One we call the P formation, the other is T formation. Okay, so after the excitation upon the absorption of the light source, the formula, the configuration of this platinum satellite gonna be changed from this P conformation to the T conformation. After the relaxation, this gonna change back to here. If you look at this structure, even if the T formation shows a little bit higher energy compared to P formation, however, this P formation shows a planar structure in these two aromatic rings. This will allow these platinum satellites stacked together by this edge aggregation. And then this edge aggregation gonna shows very interesting phenomena for this electrochemoluminescence emission. Okay, so why it's interesting? As you guys know, we have the valvin core and the phenolene group at the two ends. This is the energy level diagram for this platinum satellite. Okay, for the triplet excited state for this dolphin part, the energy is lower than that of the phenolene part. Okay, so after absorbing the sunlight, the electron was excited from the ground state to the singular excited state, followed by the intersystem crossing. We got the triplet exciton for this phenolene part. Okay, and then because the triplet valvin part shows lower energy, so the triplet energy transfer occur from the triplet excited state of a phenolene part transfer to the triplet excited state of the valvin part. However, the difference of these two energy level are too small, about 0.3 electron volt, and it's known, it's well known. If the difference of energy levels smaller than that of the 0.5 electron volt, the reverse energy transfer gonna be occur. Okay, leading to this thermally activated delay phosphorescence. This can be determined by this time result photoluminescence. So we confirm this interesting platinum satellite shows thermally activated delay phosphorescence. The advantages of this thermally activated delay phosphorescence is the lifetime can be largely extended, okay, to at least 50 times, which means the optoelectronic performance will be further enhanced by this feature, the thermally activated delay phosphorescence. Okay, so after that, we also interested in the fundamental electrochemoluminescence property. We compare the ECL emission with the photoluminescence. We found the blue shift ECL can be observed, okay, due to what? Due to the pi-pi interaction and the edge aggregation through the T formation of this platinum line. As I show you guys, this T formation is favorable for the edge aggregation, resulting in this blue shift ECL. Okay, so in terms of the in addition to the ECL, the electrochemoluminescence of these functional metal polymer materials. Now, I would like to introduce another study we are working on. We are interested in the desensitized photoelectrochemical cell. By use this desensitized photoelectrochemical cell, we can both produce the oxygen or reduction the carbon dioxide back to the carbon monoxide, or reduction from water to the hydrogen. And then we try to prepare this polymeric metal complex assembly with the study on energy and the charge transport, the surface activity and the photoredox activity. Okay, so this is the example what we design, and then we prepare this polymer backbone attached with the light absorber and the catalyst on the top of the semiconductor materials. And then with this, for the working electrode of this desensitized photoelectrochemical cell, this will allow us to produce the hydrogen and oxygen or carbon monoxide at the same time. So this project is working on, and then hope next time I can show you more promising materials and the probability for the water splitting or the carbon dioxide reduction to carbon monoxide. And then now I like to show you guys another materials we call the inorganic perovskite semiconductors. Why we are interested in hybrid perovskite? Because this perovskite shows very long diffusion length, in addition to high absorption coefficient, high charge carrier mobility, long excitant lifetime, long diffusion length, and a low excitant binding energy. Why a hybrid perovskite shows these outstanding optoelectronic properties? Because this very special crystal structure. As you can see, this is an example of a methyl ammonium lead iodide. It shows this octahedral structure, and then this special structure results in those outstanding optoelectronic devices. And then now I'd like to show you one of the solar cell architecture I'm interested in. We call the liquid junction. PEC is photoelectrochemical solar cells. These kind of solar cells with much lower cost. And then we like to use perovskite as the working electrode to generate the electricity from the sunlight. However, the hybrid perovskite can be decomposed in water and then most of them aqueous solvents. In order to apply the hybrid perovskite in liquid junction PEC solar cells, we try to investigate a series of solvent and the redox couples. Finally, we confirm dichromethane is the best solvent for the application of liquid junction PEC solar cells. And then we investigate a series of redox couples, iodide, iodine, ferrocene, ferrocenium, dimethyl, ferrocene, ferrocenium, or benzoquinone, radical anion. And then we found the benzoquinone and the benzoquinone radical anion shows the strongest photoelectrochemical response. And then we double confirm the counter electrode, the platinum counter electrode. It shows the reversible and stable cyclic photometry. Therefore, we use perovskite best working electrode combined with platinum counter electrode in this benzoquinone and radical anion to make the perovskite based liquid junction solar cells. And then we also use the Monchatti plots to make sure or to figure out the band gap of the perovskite solar cells, and then compare with the energy level of these three electrolytes. Okay, one of the important concepts for liquid junction perovskite PEC solar cell is the difference between the onset potential and the formal potential theoretically is the open voltage of the liquid junction perovskite solar cells. So this is the major reason why we use benzoquinone and the benzoquinone radical anions for the fabrication of the PEC solar cells. Okay, and then another application is for the passivation effect. As we know, aiding an access among of the lead iodide can enhance the diffusion lifetime. However, the problem is we don't know what is the optimal among of the lead iodide. We use the scanning electrochemical microscope, and then after this rapidly efficient scan, and then we confirm, okay, 2.5% of excess lead iodide shows the highest photoelectrochemical response. And then we double confirm by the PEC, and then we can make sure the 2.5% excess lead iodide shows the highest photoelectrochemical response. And then by the photophysical characterization, we also confirm again 2.5% excess lead iodide shows the longest diffusion length compared to the pristine hybrid perovskite. Okay, and then my another project, we make this one. This is heterostructure of a bismuth-based hybrid perovskite, including Ba3, Bi2, I9, and the DMA3, Bi2, I6. These two kinds of bismuth-based perovskite heterojunction. And then this is how the formation of this perovskite-based heterojunction. Okay, so this is the proposed chemical reaction. And then after confirmed by the XRD, we make sure the formation of this heterojunction. Okay, and then after we confirm by the impedance spectroscopy, it shows the lower charge separation resistance. And then due to this band gap alignment, it can further enhance the performance of a photocatalytic splitting. So this is, we found the performance is better, the stability is longer. Okay, and then we also interested in this low dimensional perovskite materials. And then after confirmed by the temperature dependent TRPL, we are sure this low dimensional, zero dimensional CS4 PBBR6 shows the stronger electronic coupling and a lower activation energy, leading to the efficient charge transport. And then through this CV at different scan rate, we confirm the diffusion coefficient and rate constant at the interface of a solid liquid interface shows the better and efficient performance. And then finally, we got the efficient ECL emission by this low dimensional hybrid perovskite. Based on this electrochemoluminescent property. And then finally, I'm gonna talk about this biophotoelectrochemical hybrid device. This photoelectrochemical hybrid device allows us to treat the waste for both wastewater or for waste. And then simultaneously in the counter electrode, the electricity can be produced or the hydrogen can be produced, depends on what kind of counter electrode we used. So this is how we did. We compare this is MR1 is bacteria. We compare the performance of the biophotoelectrode and the photoelectrode. We found that the biophotoelectrode shows the better performance. And then we also developed the new kinds of non-toxic bismuth perovskite, non-toxic hybrid perovskite, and also shows the strong PEC response. And then this is the photoelectrochemical characterization to confirm the result through this scanning electrochemical microscope. Okay, we show the promising properties for this biophotoelectrochemical hybrid device. Okay, so I'm gonna thank all my group members, collaborators, and funding resources. And then this is my group members. Okay, and then thank you for your attention. I'm happy to take any questions from the attendants. Thank you.